In the last lecture, we have discussed about the N-type semiconductor and the P-type semiconductor, and we also have discussed that there are two types of carriers in those semiconductors, the majority charge carrier and the minority charge carrier, which can be holes as well as the electrons. So in this lecture, we'll discuss about the transport mechanism of those carriers. Okay, so we'll discuss how does the current flow in a semiconductor. The flow of current in a semiconductor can be categorized into two components. One is the drift current and the other is the diffusion current. So we will see these both types of current in details in this lecture. So let's discuss this drift current first. So as the name suggests, the drift is basically you're drifting. So a force is applied and you're drifting from one end to the other end. So consider a semiconductor device. Let's consider maybe an intrinsic silicon, a pure silicon. So this is my pure silicon bar, and we know that it has holes and electrons as a charge carriers. Okay, and of course which are thermally generated. And let's apply a potential difference across the two ends of this semiconductor. A potential V is applied, and because of this there will be an electric field. The direction of the electric field will be in this direction. And because of this electric field, because the holes are positively charged, so it will move in this direction. And the electrons will be moving in the opposite direction of the electric field, definitely. Okay. So now the question will come that how will these holes and electrons move? Whether they will get accelerated or whether they will be moving with uniform velocity. So this is my electrons and this is my hole, of course. Okay. So again, the question is whether the electrons will be moving with uniform velocity or with an accelerated velocity. So basically what happens is, suppose the hole is moving or the electron is moving. So in the semiconductor, there will be these crystal atoms, right? So if the electrons moves, so they will be, because of this electric field, they will be accelerated, right? But then they will be hitting this crystal structure, the atoms. So then the velocity here, it will be 0. Then again it will get accelerated, and again it may hit some another atom, and again they may get accelerated, and again they will be stopped there by another atom. So if you see the overall motion of the electron from this end to the other end, so it is going to become a uniform velocity. So they are going to move with a uniform velocity, or in other words, what we can say is that the electrons are going to get drifted from this end to this other end with an uniform velocity. Okay, and the same thing is going to happen to the holes. The holes are going to get drifted from this end to the other end. Okay, so if you see, the velocity acquired by the holes will be directly proportional to the electric field. So the velocity acquired by the holes can be given by, so this is a drift velocity, and Vp, the holes, and let's call it as V drift. The drift velocity can be given by mu P into E. Okay, so it's directly proportional to this electric field E, and there is a constant, proportionality constant, mu P, and this mu P is called the hole mobility. Okay, so this mu P is the hole mobility. Okay, so what it means is that higher the electric field, higher will be the velocity, drift velocity acquired by the holes. Okay, And if you see the unit of this mu p is basically, we can find it out. So velocity, we know that it can be expressed as centimeter per second, and electric field, we know that it is volt by centimeter. Okay, so if we rearrange it, then we'll get the unit of this mu p as centimeter square per volt into second. So its unit is, okay, so this is the mobility, okay, whole mobility. So similarly for electrons also, we can write the, the drift velocity of the electrons, which is Vn drift. The velocity of the electron is Vn drift, and it is given by minus mu n e, minus because it is opposite to the direction of the electric field. So the electric field is in this direction, whereas the movement of electron is in the opposite direction of the electric field. So in the last class, we had discussed that electrons are more mobile, right? Electrons move at least 2.5 times faster than the holes, right? So here, if we try to find out the ratio of mu n and mu p, we will get this ratio, whatever we had discussed in the last class. So what it means is that mu n by mu p is going to become 2.5 times. So what it means is that the electrons are 2.5 times more mobile than the holes, or basically the mobility, the ability to move for the electrons is 2.5 times higher than the holes. So this ratio will become important, especially when we'll be designing some electronics circuit. So especially if we build a device which is based on the conduction of the electrons, and if you build another device which is based on the conduction of the holes. So if you want the same resistivity or same kind of property, then we should make the device which is based on the movement of holes to be 2.5 times higher than that of the electrons. Okay, so this we will be seeing in future. Of course, this is an approximate number, and with doping, this ratio also may change. Again, this also we'll be discussing in the future class. So now we have estimated the velocity of both the holes and the electrons. So now let's discuss the drift current due to the holes and the electrons. We have found out the velocity. Now we will see how to convert that velocity into current. So we'll see the drift current due to the holes and the electrons. First, we'll see the drift current due to the holes, and then we can have similar conclusion for the electrons as well. So consider a bar of silicon. So this is a silicon bar. So let's try to analyze the movement of the holes. Okay. So let me apply a potential difference between the two ends of this bar. So because of this potential be applied, there will be an electric field in this direction, and the holes will start moving from this end to the other end with a uniform velocity, right? So now we want to find the current. So the definition of the current is the amount of charge crossing a cross section in 1 second. Okay, so let's consider this cross section. So this is my cross section. Okay, of course it is something like this. Okay, so now we want to see how many charges are flowing or crossing this cross section in 1 second. Okay, and of course the holes are moving with a velocity. We know that it's a velocity. It's moving with a velocity of v drift. Of course, it will be centimeter per second. Okay, this is the unit. Okay, so that means in 1 second, the holes are going to move by vp drift centimeter. Okay, so so in 1 second the holes will move maybe to this point. Okay, in 1 second. Okay, so it has moved to this point. So what we can say is that the length covered in 1 second is this much, right? So this is also pp drift centimeter. Okay, so that means the amount of charge present in this box is the amount of charge that has crossed this cross section in 1 second. So if the area of this phase is A, then the volume of this box is going to become A into BP drift. Of course, it is in centimeter. Okay, so the amount of charge present in this box will be given by, so the amount of charge in the box is given by A into BP drift. So this is the volume, and the density is P, of course, the density of the holes is P, and charge of its hole is Q. So this much amount of, charge is present in the box which has moved from this point to this point in 1 second. Therefore, the current will be again given by the same one. Of course, here in this case this is in centimeter, but when we express this is by centimeter per second, right? This will be again current. Okay, so my IP due to the holes, the current is again here I have just rearranged it. Okay, and is equal to, if I substitute this one with the expression that I have got, basically this one mu p into E. So let's substitute this one with this expression. So it will be AQP mu p into E. Okay, so here we are very clear. A is the area of the cross section, Q is the charge of the holes, P is the density of the holes, and mu p is the mobility of the holes, and E is the electric field because of the potential V applied. Okay, so I want to get rid of this area parameter, okay, so that I don't have to every time mention this area, so that I can define a current density, which is basically this current by this area. So the current density due to the hole is given by Jp is the density, is equal to Ip by A is equal to Qp mu p into E. Okay, so this is the current density due to the holes. So similarly, I can write the current expression for the electrons. I can get this kind of expression. So for electrons, the current is given by, again, the current will be In is equal to, of course, now the negative charge is flowing. Okay, so here we have to be little careful. So this is the negative charge will be flowing, so it will be minus right. So of course, yeah, so this will be the current expression, and if I substitute this term with this one, right, mu and E, of course, now again this minus and minus will get cancelled, so minus of this one and this one will get cancelled, so finally what I'll get is AQ, sorry, this should be N, because we are talking about the density of the electrons, which is defined by N, so AQN mu N into E. Okay, so of course finally the current is positive, which is true because we know that, as we have discussed, that the electrons are going to move in this direction and the holes are going to move in this direction because of the electric field E, but both of them will give rise to the same current in this direction because the current flow or the convention of the current is opposite to the direction of the movement of the electrons. Okay, so finally, therefore, the current density due to the electrons is given by In. The current due to electrons by A is equal to Qn mu n E. Okay. So now, because both of them are in the same direction, they can be added. Okay, now since both of them, these Jp and Jn are in the same direction, so they can be added. So therefore, the total current or the total current density is given by okay, so it is Q P mu P plus N mu N into E. So this whole term is expressed as the conductivity. Okay, this term is expressed as conductivity or d by the letter sigma. So this is basically the conductivity. Or it can be expressed by the resistivity, which is rho, is equal to 1 by sigma is equal to the inverse of this one, so which is, and this is resistivity. So finally what I can write is, I can write this J total is equal to 1 by rho into E. So one may ask, how do we relate with the Ohm's law? Okay, we know that the resistivity, but how do we relate this with the Ohm's law? So this can be easily related to the Ohm's law, because we know the J total is basically the I total by A, and we know this is 1 by rho, and we know that E is basically the potential difference applied by the L. Okay, so where the V is the potential difference applied, and we know that this distance is L, right? And considering the electric field is uniform throughout this whole bar, and also that the potential difference is decreasing from this end to this end linearly, so this is considered. That's why the electric field is given by E equal to V by L. Okay, so if I just rearrange it, what I'll get is V is equal to rho L by A and into I total. Okay, and we know that this term is nothing but the resistance. Okay, so now let's discuss the diffusion current due to the holes and the electrons. So what is a diffusion current? So imagine I have a glass of water. Now if I drop an ink drop, something like this, so this ink is going to spread inside this clear water. Okay, we'll see that this is getting sprayed. So this phenomenon is called diffusion. So similar kind of phenomenon happen with the charge carrier in a semiconductor. So consider I have a silicon bar. So this is a silicon bar, okay? And by some means, let me inject some holes on this surface of the silicon, okay? Okay, so what it will happen is these holes will be here, and slowly if you see the concentration of the holes, it's going to reduce. Okay, and of course we are assuming here that we are having some mechanism by which we are taking out the holes from the other end of the bar. Okay, so the point here is, if you see the concentration profile, okay, So the holes will get diffused inside this bar, and it will have this profile. And the current will depend on this concentration profile. So this is basically the diffusion current. So more precisely, let us draw the profile of the concentration of the holes towards the direction x. So if I consider this as my x-axis, okay, so this is my x-axis, and the y-axis represents the concentration of the holes in this bar. So the concentration of the holes, it will be something like this because it's diffused here. And let's consider this concentration profile to be at px. So this is a function having a px. That means at the point here, I'll have my concentration as px at any point here. Okay. So the diffusion principle of the semiconductor states that the magnitude of the current at any point of the semiconductor is directly proportional to the slope of this concentration profile. So if you see here, I can draw a slope here. So I can draw this gradient or the slope at this point of this concentration profile, and the current will be directly proportional to this slope. Okay, the slope is given by, of course, dpx by dx. Okay, so the current is directly proportional. Okay, so the magnitude of the current at any point is proportional to the slope of the concentration profile or the gradient. So we can write IP is directly proportional to the slope, which is dpx by dx. But however, we have to be careful because you see the slope here, it is negative. Slope is negative, whereas the direction of the current, the holes will flow from the higher concentration to the lower concentration. So the holes will flow in this direction, and the direction of the current also will be in this direction. Okay, the IP will be in this direction. Okay, so we have to give a negative to cancel this negative slope. We need to use this negative, so negative will get cancelled, so IP will become positive. And of course, the current IP also will be proportional to this area A. So where this is the area of this this face of this box. Okay, so then IP also will be directly proportional to the area as well as the charge of the holes. Okay, so dpx by dx. Okay, I can introduce a proportionality constant, and I can write IP as, therefore my IP is equal to minus AQ dp, okay, dpx by dx. Okay, so where this dp is a proportionality constant, and dp is basically the diffusion constant. Okay, dp is basically the diffusion constant, or in one sense I can write this my current density. Again, just like the drift current, we want to make it independent of the area, so IP by A is equal to minus Q dp dpx by dx, where my Jp is the diffusion current density. Of course, it is like the ampere per the meter square or centimeter square. Okay, when the length is in centimeter, it is in centimeter square. And my Q, of course, is the charge of the holes, or the magnitude of the charge of the holes, and dp is the diffusion constant. Okay, so this diffusion constant is depends on the material. So for for silicon it will have a certain value, okay, and the px, as we have seen, is the concentration of the holes at x, at a point x, okay. So these are the different variables in this expression. So just like for these holes, we can get the diffusion current for the electrons as well. Again, this is the concentration profile of the electrons, and it is represented by an X. And of course, the electrons also will move from higher, from higher density to lower density. So the electrons will move in this direction. So electrons will move in this direction. However, as we know that the direction of the current will be in the opposite direction of the movement of the electrons flow. So this is the direction of the electrons, whereas this is the direction of the current, because we know that the convention of the currents due to the electrons is opposite to its motion. In case of the holes, right, the direction of the holes was in this direction, the movement holes from higher concentration to lower concentration, and the current is also in the same direction as the direction of the movement of the holes. So this is the difference between the the diffusion current by the holes and the electrons. So finally I can write the current density of the movement of the electrons as q dn dnx by dx. Note that in case of the holes there was a negative term to cancel this negative slope, right? Whereas in this case there will be no negative term, because the negative sign of this slope will be required to represent the direction of the current, okay. And this we can get the typical value of this dn for silicon. So for the holes and the electrons, the typical value of the diffusion constant is dp is equal to 12 centimeter square per second. This is for the holes, and for electrons it is 35 centimeter square per second, okay. So this is all about the diffusion current because of the difference in the concentration either for the electrons and for the holes. So now if we try to find the diffusion constant and the mobility, we'll come up with a very nice relation. This is called the Einstein relation. So suppose if I divide the diffusion constant of the electrons with the mobility of the electrons, this ratio will come out to be kT by Q. Again, K is the Boltzmann's constant, T is the temperature, Q. So if you observe this ratio is not dependent on any material parameter, because K is a constant, Q is a constant. It is just dependent on the temperature. So the diffusion constant and the mobility, if we find out this ratio, it becomes independent of the material parameter. This ratio is sometimes called as Vt. This Vt has a unit of volts, but note that this Vt doesn't represent any physical voltage or potential difference. It's just a constant. And this Vt, I should say that comes into picture whenever we will be, or this Vt will come into picture whenever we'll discuss the PN junction diodes, okay. So this constant is going to keep coming. And this Vt, if we find out at room temperature, it happens to be approximately 26 millivolt, or T equal to 300 Kelvin, okay. This Vt happens to be approximately 26 millivolt. So we need to remember this value, because this Vt at room temperature will come again and again, especially when you are discussing the p-n junction diodes. Okay, in the next class, we will discuss what happens when the P and N, these two semiconductors, are combined together, and we will discuss about the p-n junctions and the p-n junction diodes.